I will talk about why this is an interesting challenge we should work on and our first results towards finding a solution for it. Okay. Yeah. So, as you might know, correspondence search aims to identify the same points in different images, which is a core task in many mapping and navigation methods. In the underwater domain, more specifically, correspondence search is required for loop closure detections or location recognitions or across-track matchings, for example, in seafloor surveys by autonomous underwater vehicle like the AUV Anton you can see here in this small video. And in this short video, we'll also get an impression that correspondence search on underwater images is more challenging than it is in air. The interaction of light with water and particles in it lets underwater images appear very differently to images of people or animals or things we are used to in our urban or natural environment. This is due to scattering and absorption that distort the color and the contrast dependent on the distance between camera and objects. Also, artificial lighting, which is necessary due to more and more absence of natural light the deeper a camera is placed in the sea. This introduces co-moving light pattern in the images. And when you think about how state-of-the-art methods rely on the distribution of image gradients, you can get an intuition about why the available methods struggle in finding corresponding points in those underwater images. This image pair, for example, shows to you how the result of a root sift matching on it is affected by different contrast and lighting pattern between the images. So let me first here locate our work in the broad context of image processing. Our aim is to achieve feature extraction for matching correspondences robustly, like we are used to for in-air images, for example, from the famous SIFT algorithm. But of course, we want to do this in the water. And as convolutional neural networks have shown some significant performance improvements in image processing where we lack proper physical models, we want to apply CNN for this task. The LFNet by Ona et al. Or the D2Net by Dusmano et al. Are only two examples where CNNs achieved high scores in feature extraction tasks with in-air imagery. And especially the D2Net is of particular interest here because Dusmano and his colleagues trained their feature extractor for challenging image appearances in air, like day-night differences, motion blur, very wide baselines. And we think that underwater correspondence search could benefit from their work. So we choose the D2Net as base for our work. And also close to our work in terms of tackling underwater images is the work by Yu et al., who trained CNNs for object detection, or the work of Irfan et al., who use transfer learning with CNNs in classification tasks. But to our best knowledge, feature extraction on underwater images is still an open task on which we want to focus here. So let us briefly look into some more details on the data and the model structure. The D2Net, first of all, is based on the VGG16 model, and their training is initialized by a pre-training on the ImageNet database. To get a model for feature extraction instead of classification, which is the original purpose of the VGG16 networks, the D2Net authors cut off the fully connected layers and the last convolutional layer, and the fine-tuning towards very challenging image appearances is then trained on the Megadeth database. This includes touristic imagery, along with, and that is important for training, ground truth correspondences that they obtain from structure from motion. In order to fine-tune with this data, the last convolutional layer was optimized, while the remaining network sticks to the ImageNet class initialization. And what we did to adapt this strategy to underwater images is yet another fine-tuning step with about 2,400 samples of underwater images on the same last convolutional layer of the D2Net. So if I say another fine-tuning step, then I refer to version B of our trained models. We also trained another version where we did the fine-tuning directly on top of the plain ImageNet initialization. So just for simplification, I refer to the models as version A and B respectively in the following. So, but now we still need the underwater images to train our models. And while there are plenty of data sets that include underwater imagery somehow, and there also exist a lot of images of seafloor surveys, of course, those data all lack the pixel level ground truth correspondences we need for training. And this is why we simulated the images with the open source ray tracing software Mitsuba. From the ray tracing calculations, from the positions where simulated light rays hit the surface of background 3D models, we can obtain the coordinates of the scene that serve then as ground truth correspondences for our dataset. And to get close to photorealistic images, we use high-resolution 3D models of sand, mountain, gravel scenes, which all show content that is semantically similar to seafloor. And then we submerge those 3D scenes into water by adding oceanic light attenuation models for the surrounding volumes and parameterizing it with real oceanographic measurements that was obtained by Jelf in the 70s, who classified different water type by its color and turbidity. So, and this is a collection of sample images from the dataset we get. And here you can see the diversity of simulated images. We model different light configuration, different types and turbidities of water on 12 different scenes. So as we now have all together the idea, the model, and the data, I would tell you about some of our findings we got from this approach. So the first of our findings addresses, first of all, the feasibility of fine-tuning the chosen network with underwater images. And this is because the applied loss function, the triplet margin ranking loss, tends to model collapses if image features become hardly distinguishable from each other. As a measure for the tendency to model collapses, we chose the mean loss at the initial training epoch, which shall below the threshold of 1. The details of the mathematical reasoning behind this analysis you can find, of course, in our paper. However, the important point to notice here is to observe which image transformations still yield features that are distinguishable enough to get proper initial training conditions. So in terms of our stability criterion, this means which transformation result in an initial loss that remain below the critical threshold. And you can see in those figures that we investigated for different transformations, which are translation, rotation, scaling, and the variation of the mean free path of light and water, which serves as a measure for the water turbidity, or in other words, how dominant the water affects the image appearance. And we see why the training stability is not affected by the translations and turbidity of the water. It is in fact by rotations over 40 degrees and scalings larger than the factor of 1.5. And it is therefore not really possible to do the fine-tuning in the proposed manner with the data set that includes larger image rotations or scalings. So we prepared our data set accordingly. And with that, we trained the models and we evaluated them by the mean matching accuracy on a different data set of simulated images. You can see accuracies for varying thresholds of tolerated reprojection errors here. And you can observe at first that all learned models reach an accuracy which is comparable with the state-of-the-art non-learning method, root-sift, we chose here, only if a reprojection error of 4 to 5 pixels is tolerated. And this is most likely due to downscaling images to fit the network input size resolution. The resulting feature map is therefore also on lower resolution, and interpolating to the original image resolution causes the observed inaccuracies. And as a second, we can see slightly increased matching accuracy of the underwater fine-tuning compared to the original D2Net. Our fine-tuning that also includes the D2Net pre-training on this challenging Megadeth dataset shows the best performance of the evaluated models. But of course, the improvements for now are quite small. So what did we learn from our experiments? First, for larger image rotations and scalings in the fine-tuning dataset, the training can become unstable. And that is not a trivial constraint in the underwater domain, because the imaging settings are not necessarily bound to gravity direction like they usually are in air images. And therefore, we recommend adjustments toward rotation invariance when applying CNNs in underwater tasks, or the orientation to the same direction of images already before the training. And secondly, our matching results indicate that cross-domain transfer learning could be a suitable approach towards robust correspondence search. But of course, further experiments with larger data sets, maybe different networks types, and of course, deeper fine-tuning will be necessary to get more insight into the still existing challenges. Yes, and with this, I'm at the end of my talk. Thanks for your attention.
Is there any questions? Okay, I have a question. I think that simulated images are very important in this context. What do you think are the challenges of using this kind of simulated images?
So what the challenges are when we use those images?
Yes.
Yes, of course, we have to be careful that the simulated underwater effects, or that the effects we want to train with the network to get robustness towards them, are realistically appear in the images we simulate. So we have to get the images really realistically and close to the physical behavior of images when we do seafloor surveys to achieve those robustness. And of course, we have to be careful with some non-idealities or artifacts we might get when we use artificial scenes or not really photographs. But I'm pretty convinced that with our ray tracing approach, we are very close to really physical modeling those appearances.
Okay, thank you. So thank you again, Patricia, and thank you. Okay, so we move to the second talk from underwater image enhancement using pre-trained transformer. The speaker is Saeed Javed, and is remote. Are you there, Saeed? Saeed?
Is not in the session.
No.
We don't see him among the viewers.
I don't know. We
have a video.
Okay.
If you want to just one more.
If he's not here, maybe we can put the video.
Just 1 second. No, he hasn't uploaded the video on the website.
Okay, so we can move to the next talk from Kevin Kosher.
He's here, yeah.
Yes. And the title is Robust Human Identifiable Makers for Absolute Relocalization of Underwater Robots in Marine Data Science Applications. Are you here, Kevin? Can you
Yes,
hear me?
hello Alessio, I'm
Okay.
here. Would you play back my video or how are we doing this?
No, if you can give the talk, is better.
Okay, just one moment. Welcome to our presentation of... Can you hear that?
Yes, please.
On visual absolute relocalization of underwater robots. And our motivation for this work is in coastal monitoring, where we want to look at the change of seagrass coverage. So this is in the context of blue carbon. But there are also bacterial mats appearing and disappearing, deposition of sediment, and also here in our coast, also we have a lot of munitions from the World War still, which were disposed here, and we want to monitor also the munitions. And on the top right, you can see an AUV that we are using here with a downward-looking camera, and the bottom shows you example imagery of these of the AUV. And this is a very good day, the material here. So we have up to 2-meter visibility, but sometimes it's much more turbid. So it's really challenging, these visual observation in the coastal waters. And we have some relocalization issues, but let me just show you how we approach this. Basically, we generate, by structure from motion techniques, we generate 3-dimensional maps of the seafloor. And then we want to come back after 1 day or 1 week or 1 month or 1 year and check what has changed. But the problem is we don't have absolute position information really. So the only source is GPS before the robot dives down. But there is some GPS uncertainty. We have some drift of our navigation system over time. So we really want some visual anchors, visual relocalization, ideally at centimeter precision. And we start now with the help of optical markers, and ultimately we'd like to do it without markers. Yeah, we are here if you look in the right picture, we are here in the north of Germany at the Baltic Sea, in the city of Kiel, and in the Kiel fjord, we have a small test area where we put some markers in the ground. Now I'd like to talk about the design and why we chose markers. So we really need to detect markers under harsh conditions. So it's partial occlusion. We have a lot of floating particles, as you can see here. There is sediment falling on top of the markers. In the bottom right, for instance, there is algae and stuff is growing on the markers. So we have to deal with the occlusion essentially. And we want to detect the markers also in distorted fisheye lenses, because we have these wide angle lenses on the robots for mapping. And depending on the visibility, we want to fly the robots at different altitudes. So we need them to be detected at different scales, essentially. And there are many markers in the literature from augmented reality largely. And also some were used for underwater marker experiments already. But our situation is a little bit different because we want really long-term deployments with strong occlusions. And also these markers here, they can be made robust, but mostly the interior pattern, the bit code can be made redundant. But if the outer part is occluded, then the marker will not be detected at all. So this is a problem. We want to, therefore, we decided to rely on markers that contain, let's say, visual features. So we're using a feature-based approach here that was used for camera calibration by Lee et al. In 2013. And essentially the idea is to reverse engineer what the SIP detector does. So we build an image pyramid, and at each level we create structures or random dots at different scales, basically. Then we combine all of that, and this resulting combined image has a lot of features in different sizes, so can be detected from different distances. Then you can just use standard pose estimation, robust pose estimation methods for this. Here's an example in the top right. So we have all the different layers with different scales of noise, and then we add also another layer, a very coarse resolution layer with a handwritten digit, and combine everything to such a picture. And this enables us also that we can, as humans, we can re-identify the marker. It's a big effort for us to go out with the ship, deploy the robot, and so on. So if you capture data, it's important that you can also look at the data and work with the data. So the data is very expensive, so to say. So that's why we also wanted to be possible that humans work with that data. So we print these markers in 30 by 30 centimeter size and then mount them on a paving stone. So this is really heavy and it will not swim away. So they really lie on the ground. And they are released by a ship that basically in 10-meter water. And the texture we give to the printer, we detect also features inside the texture, and we convert the detected texture coordinates of the features to 3D points because we know the marker size, and then we can just convert it to points in the marker coordinate system. This gives us a set of descriptors with 3D points for every marker. So we have kind of a marker database. And you can see we're not just making one of the markers, but we have a lot of digits, and we are very careful that these digits are not symmetric in a way to avoid confusions of 90 degrees or 180 degrees rotations. And you can do it black and white, so that we have overall we get like 20 markers just for testing. And now I want to show you how we're doing the pose estimation based on the markers. So we start with a standard method to increase the contrast of our image. So you can see the water is very green and murky, and we use the Klahe method to do the contrast enhancement, and that gives us more features here. And then basically we detect some features in this image and we match them to our markers. And then we can do some classical let's say heuristics to improve the set of features like the ratio test and so on, and we keep the best 50 matches. And based on these matches, as you can see here on the right hand side, most of them are good already, but there are still some outliers. And then we want to do pose estimation, but the problem is that the image is fisheye image. So you can undistort the image, but it's too expensive. And so we just undistort the feature positions to raise. And then we can use robust pose estimation methods on these rays. We have 2D 3D correspondences to the marker coordinate system. And then we end up from the RenSec inlier, we can optimize them. So we end up with the pose of the marker, basically, as you can see here. And all the dashed lines here are 10 centimeters long. So you get an idea how far away we are from the marker here. This is another example where we are at low altitude. So you can see this is 10, 20, 30, 40, 50 centimeters. I don't know, maybe we are 1 meter above the marker here. And it's really a lot of sediment on the marker, so it's difficult for you to do that. But still in the surrounding, there were some features that could be matched, and we found the markers. And then we want to look more systematically on the occlusion and look at the top right image first here. So we put onto the marker, we put just some gray square, so it's blocked. We cannot see it anymore. Here it's like 90%, and maybe here this is 70%. And these images, it's less occluded. And we repeated that several times and also tried it on synthetic data with different marker poses. And then what you can see basically is up to 70%, everything works nice and we get good pose information. And if you have more than 70% occlusion, then the marker detection and pose estimation will break down. But for Aruco markers, it breaks down almost immediately. So if you cannot reliably detect the border, then it will not be detected in the, at least in the standard OpenCV implementation. If you do another implementation, find that. We put the markers then here in the Kiel fjord in 3 rows. As you can see here, it was like an 8-meter water depth by boat, and because there is no absolute underwater localization. We are not super sure about the positions of the markers. So we want to estimate them by repeated dives and going with the robot over the markers and then checking what's the estimated position. And for that, you can imagine the robot knows where it is in the world, at least above the water. It can get GPS, then it can do dead reckoning below the water surface. We have a number of transformations from world to robot, robot to camera, camera to marker. And then we can chain all of them and check what's the position and what's the consistency of the detected marker positions. And if we do that for same day observations here, but repeated dive missions after a few hours, we can see mission 1, we got this color on the top right here, we got this position. Mission 2, we got this position. Mission 3, this position. Mission 4 here. And every mission we saw the marker multiple times going back and forth over the marker. So you can see they all the same colors cluster. So there is little noise between the robot motion direction, let's say, but between the dives there is significant offsets, and we believe this is because of the GNSS uncertainty, because we see different satellites when the robot comes back to the surface. There's also potentially sensor drift, and if you go back after a long time, maybe also water level, high tide, low tide might play a role, and theoretically also marker movements. But essentially, if you want to rely on GPS for absolute positioning, then you can only expect a few meters accuracy on the sea floor. And if you have 1 meter visibility, this is not helpful for change detection. Then finally, we also plotted where do we see the markers and how does that fit to our original plans. And we see that all the markers are after 1 year still there where we expect them to be, but many of the markers we cannot detect anymore. Yeah, that's how far we are. So this is still ongoing work. Just a short repetition. We want relocalization, visual relocalization under harsh conditions with good precision, and we created these markers basically, and then you can just do pose estimation for getting the pose. And up to 70% they are useful, and they are even more useful because GPS error is too big for monitoring applications. But we still have some future work to do, so we need to clean the markers because they will be so much overgrown, in particular in the summer, that they are not effective anymore. And we want a live implementation to correct the live robot position. This was all done like afterwards evaluation, what we've seen here. And after everything is solved with the markers, we want to work towards natural relocalization using just the features which are there. But it's difficult to find and decide which features can be used after several months or 1 year for relocalization. Certainly not seagrass, and probably not the seashells or so. Yeah. Thanks for your attention.
Questions? Okay, I have a question for you. Do you think that is it possible to learn some degradation pattern in order to study how these markers are covered with sand or other things underwater?
Yeah, I think that could be an interesting idea to kind of, you need a lot of training samples, I guess. So you have, maybe we can pick some sand or sediment and then pour it on top of the marker and take a lot of pictures. Or maybe that could also be simulated by rendering or so. But I think that could be an interesting option to also kind of learn the occlusion. That's a good point, yeah.
Are you aware of any study about this topic on learning this occlusion pattern or degradation pattern?
No, currently I'm not aware.
Okay. Thank you, Kevin. Thank you very much for your interesting talk. And we move to the next. We go back to the second that should be now online. Sajid, are you there?
He's coming. There's a substitute for Sajid, a colleague of him who will present.
Okay.
Hello?
No, he's him.
Okay. Can you hear me?
Yes, sorry for the
Yes.
mistake. I guess I just misstated the name, so
Okay, don't worry. So the paper is underwater image enhancement using pre-trained transformer.
yeah, correct. So can you see my screen?
Yes, yes, please go. Okay.
Welcome to my presentation. My name is Sajid, and I'm presenting our work underwater image enhancement using pre-trained transformer. So why underwater imaging is important? So we need underwater imaging for many things, like underwater autonomous navigation. Since water block greatly the signals, we can't directly control the underwater vehicles directly. So we need image enhancement to increase the quality of the images so the navigation network can work properly. Also, it's used for many applications for marine studies, from studying the population of fishes to studying the migration of fishes also. And it's a challenging environment since it produces color attenuation and light scattering, which decrease the quality of the image and shifts the colors to different colors. So previous work was treating this problem using dark channel pair approach, which estimate the backlight and the light scattering, but it's limited by the estimation of those factors. Other approaches used CNNs, generative adversarial network, and other networks, but no work have been done using image transformers. So we are exploring the capabilities of this type of network on underwater images. So image transformers were originally made for natural language processing. And then later on, image transformers were introduced. So image transformers usually require a high number of calculations, which increase the computational cost. And a way to avoid that is by dividing the image to patches instead of treating them as in pixel-wise, which will decrease the computational cost. So we are basing our work on a pre-trained image enhancement network, which has 4 different tasks: denoising images, deraining images, and 2 level of upscaling. So this is a general schematic of the network. It has 4 heads, 1 for each task, and then we have the transformer network, and then we have the tails, which produce the clean images. So we have modified this network to work with our goal. So first of all, we replaced the heads with ones that extract the features from the images. And then we have the same transformer network, the encoder and the decoder. And finally, we have the tails, which output the image. So this is an example for the pre-trained network, which was dealing with denoise. So you can see that it has a very good performance and removing all the noise from the image. So we fine-tuned this model on the YOFU 120 dataset, which give 1,500 pairs of training images and 124 evaluation. So this dataset is mainly for 3 tasks: for upscaling, for dehazing the images, and for classification, so or object detection. So we just use the part where we do the image enhancement. So this is a general graph of the loss during 5 epochs of training. So you can see that it falls very quickly in the first epoch, but it continues to with a lowering trend in the following epochs. And the reason why we kept training for more than 1 epoch is that even though the loss was low in the first epoch, the results were not as good as the 5th epoch. So to compare our results with other networks, here is the PSNR and SSIM values. So we can see that the SSIM values, it got the highest one with 0.9. As for PSNR, it did not get a very good score, and that we can say that it's due to the smoothing effect of the denoising level. So we believe that with the further training, it could get a better results. But training, as I said, training transformer takes a long time. So we settled with this result. For practical results, we can see here some images. So the top row is the input, the middle row is the output, and the bottom row is the ground truth. So we can see that it can remove the haze pretty well from most of the images. And it works the best with the images with greenish tint. So you can see, for example, in this plant, it restored most of the colors successfully, and it got even a better result than the ground truth. But in some images, which is like have a bluish tint, it did not perform as good as it performed with the green tint. We can also notice that there is a loss of details, a slight loss of details in the images. And that's just like we said, due to the smoothing effects. So those are the references for the paper. And yeah, that's pretty much it. Any questions?
Okay. Any questions?
Maybe can I ask a question?
Sure.
Yes, sure.
Please.
So thank you for the nice talk. So on slide 11, you showed that the result is even better than the ground truth. Maybe can you explain what's the ground truth? How is it obtained? And it doesn't look like the underwater effects are fully removed or so. So maybe you can tell a little bit about this.
So the ground truth was obtained manually. So a team of people was editing the images to restore a pretty clean image. But we believe that the network have learned the thing that makes the images of a low quality. So one thing that we can notice on most of the underwater images is the green tint. So it was removing the green tint from the images. And we can say that the quality is low, but the colors are very close to what it would have been without water. So yeah.
Okay, thank you.
You're welcome.
Okay. Other questions? Okay. Thank you very much. And
Welcome.
the next talk is from Maggio that should be here. Okay, he's coming. And the title is Prediction of Fish Location by Combining Fisheries Data and Sea Bottom Temperature Forecasting. Please, Maggio.
Okay. Hi everyone, my name is Matteo Spici, and I'm very happy to be here to present the work we did with my colleagues Klaas and Sophie within the European project CIBEL. So the objective of this work is to predict the fish location on the sea. So we defined the grid. So in our implementation, it's a grid of 80 by 80. And at each point of this grid, we want to predict the probability of presence of fish. So for okay. So why we did this? For several reasons. One reason are economic effects, because if the fishermen know where to go on the sea, they can reduce the fuel used by the vessels. And of course, if the fishermen know where the sea, the search time can be reduced, and the fishing period can be also reduced. And there are also environmental effects. If we know efficiently where the fishes are on the sea, we can manage the fish stock in an efficient way. And of course, if we reduce the fuel, we reduce also the carbon emissions. So for this work, we had access to a data set collected by the marine environment researcher in Belgium. And in this data set, so there are many informations, and there are also information about amount of fish caught. So we have an history of the amount of fish caught at a specific location, so latitude, longitude, and at a specific date. So with this kind of data, we can construct a machine learning model, and with this model, we can construct our probability grid by calling the model at each point of the grid, and we have the probability of presence of fish on this grid. But for this work, we decided to go one step further, because many studies in the marine literature showed that there is a link between the environmental factors, such as the temperature of the sea, for example, and the presence of fishes. So we decided to build another model able to predict the temperature of the sea. So in our study, we use the sea bottom temperature. We also build another model with the fisheries data I presented at the previous slide. And by combining the prediction of the first model and the second model, we can have a higher accuracy for the fish prediction. So I will detail the first model, and after this, the second model, I will show you the performance of our approach. So the first model for the sea bottom temperature prediction has been built using satellite data. So we collected sea bottom temperature satellite data from the Copernicus project, the European Copernicus project. And we got more of 5,000 successive days of temperature from 2006 to 2021. And each temperature map can be seen as an image with one color channel. So we did some data processing. We crop the temperature maps to our area of interest. We made some normalization, and in the initial data set, the land was coded using not a number value, and in our work, we coded this land area by a negative value, -5. And I will show you how this choice implies in terms of performance. So in the computer vision literature, there are many models designed to predict successive frames on a video. So the idea is to put some frame as input, and the model predicts the next frames. So we used such model called PredRNN++. It was published at ICLR in 2018, and so yes, the model was designed for video frame, but in our work we decided to retrain this model, but with satellite data. So yeah, we use this pipeline. So basically, we configured the model in order to have a sequence of 4 days as input, and we train the model to predict the 4 next days, the 4 next sea bottom temperature. So we use loss function L1 plus L2. We tested several loss functions, and this one got the best result. So the performance of the temperature forecast model. So to assess the performance of this model, we use two metrics: the root mean squared error and the mean absolute error. So we have 4 input images, and we want to evaluate the quality of the prediction of the 4 output images. So we compared the performance of the prediction with the last day we know in the sequence, because the difference in terms of temperature between 2 successive days the difference is very low. So it is important to be sure that the prediction of our model is better than the last day we know, and it is. It is the case if you so in orange we have the error with the last day we know, and in blue it's the performance between the prediction and the ground truth. So as you can see, for example, for the RMSC for day 1, the prediction of the model is 14% better than the last no day, and for day 4, it's 26% better. So, yeah, so the predictions are better than the last no day, and we'll show at the end of the presentation that the power of forecasting of our model is sufficient to increase the performance of the fish predictions. So another view of the error here we have the root mean squared error for each point of the grid. So of course for day 1 the error are lower than for day 4, but it is interesting to see that the error are well distributed on the grid. The errors are not located only at the interface between the land and the sea. So this this suggests that our approach to code the land value with a negative value is efficient. Okay, so now the second model. So the second model was trained on the fisheries data, the history of fish caught on the North Sea. So we have close to 2 million of observations for 2006 to 2021. And we, in this study, we are interested in two species of fish, so the sole and the plaice. So we built two models, one model for the sole and one model for the plaice, using a gradient boosting tree algorithm. So in this tab you have the features we used. So for training the model, we use the bottom temperature directly from the satellite image, from the ground truth, and of course for the prediction we used the predicted value by the forecasting algorithm for temperature. So yeah, so basically to output the probability map, here we have the algorithm. So we can predict the temperature for 4 days. So to predict for the day 1, for day D, for day +1 to day +4, we need the satellite images from the previous 4 days. We predict temperature for day +1 to day +4. And with this temperature, we can apply the fish prediction algorithm at each point of the grid on the four grids, and we have the prediction maps. Okay, so now the performance. So we assess the performance of the two models, so for the sole and for the plaice. So in orange, you have the accuracy of the model using the temperature, but the ground truth temperature, not directly from the satellite image. It's the maximum performance possible in our implementation. In red, you have the performance of the model without the temperature. So we trained a model only with the fisheries data, without temperature. So as you can see, using temperature has an impact of the performance. For example, for place, we have 86% of F1 score, and we have 82% for if we use temperature. And in green, this is the performance of the model when we use the day predicted by our algorithm. So, as you can see, the performance when we use the predicted temperature, the performances are very close to the performance when we use the ground truth temperature in orange. So this suggests that the quality of the prediction of our forecasting model, of forecasting temperature model, is sufficient to have good result and to have result very close to the maximum performance possible in our implementation. Okay, so this concludes my talk. So we showed two things. So the first is we can use a recurrent neural network designed to predict frame on a video to predict environmental factors such as sea bottom temperature, and using an environmental feature, so the temperature of the sea, for example, can help a model designed to predict fish and can increase the performance of the prediction. Thank you very much for your attention.
Thank you, Maggio. Please.
Thank you for your talk. I had a question about a baseline. I don't know how quickly the fish population moves in 4 days. Do you have some idea of what would be the prediction score if you just use the data you got for today and use it for tomorrow? What's the kind of baseline precision you get in that case? If you just assume it's constant.
So our baseline are the fisheries data. So we use the data, the information collected by the fishermen at day D.
Yeah, and if you just assume that nothing will change and tomorrow will be the same as today, so without using any neural network, what's the kind of precision you get? So what's the improvement you get by using these models?
So
if you show your slide with the results.
Yeah, this one, yeah.
Well, sorry, I don't see it. Yeah, okay.
Okay, yeah.
So here you see 80% F1 score. And what do you get if you don't use a model? If you just assume it's the same on day 4 as today? Or as yesterday?
You mean if you consider that the temperature don't change?
Don't change at all, or the amount of fish stays the same? I mean, what's the time scale of variation of these fish?
Okay. If we did some evaluation of this, and yes, it's important to have for example the prediction of the model of temperature, because if you made some slight change of the temperature or something like this, the performance decreases.
Okay, thank you. Other questions? Okay, just one question. Do you think it is possible to build a general model not specific for a given fish with this technique? It's meaningful, or it's...
But we observe that the dynamic of the fish are very dependent of the species. So yeah, I think it should be difficult to have a general model, or perhaps if we add some other information for a kind of fish, for example. But but it's for these reasons that we made several models, because there are many differences here.
Thank you very much.
Thank you.
So we move to the next talk. Please, Luca Carlino is here, and the talk is Ship Detection and Tracking based on a custom aerial dataset.
Okay. So thank you very much for being here. I'm going to present our paper, which is Ship Detection and Tracking based on a custom aerial dataset. This was done in collaboration with Appia. You can see the authors from Appia here, which is a company from Lecce. And my name is Luca Carlino. I am from Fincantieri Nextech. This was done as a research project for the Marine project, which is a project regarding unmanned ships. I will talk about it later. So, in my presentation, we're going to see a project outline, the goals of our research. I'll give you then some background, the analysis of what is publicly available, the specific of the dataset construction, the training process, and then the results. So, the objective of a Marine project is the development and the validation of several solutions for an unmanned platform, which you can see here. It's the Teseo-1 ship. This was also tested last year. We have already performed and presented several papers regarding our research results regarding the unmanned part of the project. In this study, we will focus on the processing aspects, in particular the image processing aspects of images extracted from an unmanned aerial vehicle. So you basically have a drone which is on top of the ship. The drone looks down on the ship, and then we can do several kind of processing for the images captured and the videos also captured by the drone. This is aimed to then be fed to a multi-sensor data fusion process, which then will feed its results to a collision avoidance algorithm, which is very important for unmanned ships. So, the detection and tracking of ships from aerial images is a very challenging task. There are relatively few data sets which are available. Marine data in general is very difficult to acquire, and for several reasons, like also safety, and most images are like for military ships and so on and so forth. So the main objectives of our research, which we are presenting here, is the construction of a very customized dataset, which I will show you later some images, and the evaluation of the performance of the state-of-the-art algorithm for our customized dataset. We will use a data-centric artificial intelligence approach, which basically involves building artificial intelligence systems with quality data, with a focus on ensuring that the data clearly conveys what the artificial intelligence must learn during the training process. So you can see here, these are general schemes for the YOLO v4 architecture and the deep sort architecture, which will then be used for the detection and tracking of the ships, with the references down here. So regarding what is publicly available, there are some sources of datasets, which you can see here. for example, the Seagull dataset and also the Masati dataset. And as you can see, the ships here are in very kind of different scenarios. There are isolated ships, there are ship near others, there are ships in very crowded areas. Sometimes the image of the ship is very big, sometimes it's very small, and so on and so forth. So here in these other datasets, there are also pleasure and merchant ships, which we have taken from the sources which are listed here. And we have also acquired the images on the field during our experiments. So these are the details of the hardware. In particular, we used this kind of drones, and which are equipped with this camera, which is a quite good camera. I'm not going to go into the very specific of the hardware. I'm going now to explain the construction of the dataset just as a general overview. So first we did, of course, a data selection process. Then we cropped the images and made several adjustments. Most of them were done manually. Then we also resized the images, and we used the data augmentation techniques. And finally, we did the labeling. This was done almost entirely manually, again. And finally, we obtained our customized dataset. So the main characteristics of our dataset are that it's more than 1,000 images, and about 50 of them are acquired with our field experiments. And the object of interest, such as, for example, other ships, are labeled manually by human operator. And different types of object of interest were observed, as you can see here. So, as I also told you before, there are very different kinds of images for ships, such as in the open sea, isolated, close to others, and so on, with or without wake. So this was a quite challenging task to find the best data set which could get the best training for the artificial intelligence in order then to generalize the testing set. As usual, we did the dataset split with a training set and a test set. So this is the configuration that we used for our training process. You can see here the hyperparameters, also the hardwares and the metrics that we obtained. And as you can see here in the picture, it's the loss function. We obtained the results which were considered quite good for our specific application. So after that, we did also the detection and tracking, which was our original aim. So this was ship detection was done on the video captured in the field by the drone. This was performed with 35 frames per second. And as you can, I don't know, no, it's probably, no, you cannot see very clearly, but the probabilities were quite tight. So we identified correctly the object of interest in our pictures. While we also did the tracking, this was performed with 28 frames per second, and we basically did in our experiment was to do real-time tracking of the ship where the drone was flying above the ship. So, in this research, we have presented that we have constructed a very particular and customized large data set. We have presented the results obtained for the training of the YOLO4 neural network with our customized data set. And we also presented the results of the detection and tracking acquired by the unmanned aerial vehicle used in our experiments. Regarding our future work, what we will do is an analysis of additional real data from different scenarios in order to verify that all the training and adequacy of the training asset and the behavior of the network in general was correct. Thank you very much for your attentions. And if you have any questions. Thank you.
Thank you, Luca. Any question?
Thank you for the presentation, Luca. You didn't give us details about the tracking. I was interested in, because we have a similar work on drone detection.
Yes, so for the tracking, since we did not perform until now a very large number of experiments, I'm not going to present specific metrics because they will be not much accurate because we did not perform a large enough number of experiments. That's why. So we still, yes, the Marine project is still not over. In fact, during this summer, we will perform additional tracking tests.
What are you planning? My question was, what are you planning as not the results, but what methodology? What YOLO? You will also use YOLO for the tracking, or?
Yeah, YOLO and deep sort. Yes, yes, absolutely.
Okay, thank you.
Okay. Other questions? Okay. Thank you, Luca.
Thank you.
And the last talk is on the evaluation of two methods applied to the morphometry of linear dunes from Leonardo Emmendorfer. That should be online. Oh, hey. Hi.
Thank you.
Can you
Thank
hear
you very
me?
much.
Okay.
Can you hear me?
Yes.
Okay, I'll try to play my video. Just 1 second. Can you see my screen?
Yes.
Hello, my name is Leonardo, and this presentation is about an evaluation of two methods applied to the morphometry of linear dunes. Do you hear the audio, please? The outline of the presentation is as follows. First, we present the aim of the paper. Then we review about linear dunes and the morphological features studied here. Next, we present the dataset adopted and the annotation process. Then we present the methods we used. Then we show the results, and finally we move to the conclusions. The paper investigates two approaches for the estimation of morphological features from RGB images of linear dunes. The features are the orientation, which is the angle between the parallel ridges and a reference vector in a standard basis, and the distance between parallel ridges. The formation process of sand dunes depends on diverse factors, including the type of wind and the size of grains. This allows the formation of diverse types of sand dunes. Linear or longitudinal dunes are composed by parallel ridges which elongate in the direction of the prevailing winds. We consider two morphological features. The first is the orientation of the ridges, and the second is the wavelength, which is the distance between two subsequent parallel ridges. We use those 20 linear dune images as our dataset. All images are available from public repositories. The annotation process was very simple. For each image, we measured the angle between each ridge and a fixed vector. Then we take the average and obtain the orientation of the dune image considered. Then we measure the distance between parallel ridges, compute the average between distances, and this results the wavelength of the image. Using the radon transform, we represent all possible projections of the dune image into a single dimensional signal. We find the orientation of each image by maximizing the amplitude from the discrete Fourier transform of the radon transform from the dune image. All orientations and all frequencies are considered. The optimal frequency resulting from this process is also used for computing the wavelength of the dune image. As an alternative, we also use the method based on autocorrelation. Here we maximize the autocorrelation of the radon transform, considering all orientations and all legs, except the first legs. This results the orientation of the image and also the optimal leg. This optimal lag is considered as the wavelength of the dune image. Now we move to the results. The DFT-based method was better at estimating the wavelength of the images when considering the average error. When considering the orientation, the autocorrelation-based method was slightly better. And finally, we present the conclusions. So the DFT-based method with Radon was better when estimating the dune wavelength, while the autocorrelation-based method, also with Radon transform, was slightly superior when estimating the dune orientation for this small data set. So the data set is really small, but we're planning to build a greater data set with a higher number of images, which will be available in the future. Thank you very much for your time, and I am available for questions.
Any question? Okay. I have 2 questions. If you can outline some application fields of this technique. And the second one is if you think that the fish that you use for extracting ridges can be used for a sort of a classification task, and so automatic classification of images that you have labeled manually, no, for this work.
Yes, thank you very much for your questions. Yes, we are currently applying both techniques for waves, water waves in the sea, which are similar to dunes in the sense that there are also ridges which can be detected using the same techniques. And the second question, yes, I believe we can apply the same methods to some other types of images, of environmental images, for sure.
Okay, thank you very much again. Okay, so thank you, Leonardo. So the session is over. I want to thank you, all the authors that have submitted works, and you for attending this session. Just one last remark. Our group at the University of Partenope with the group of Kevin Koster that give the talk are applying for a special issue on these topics. So if you want to stay updated on for a possible submission, you can contact me by email, and I will keep you updated for this special issue on the same thematic. Okay? Thank you again, and have a nice lunch.